everybody. How's it going? Hopefully you've been able to at least get outside now, which I don't know about you, but for me personally, definitely makes this whole being quarantined thing a heck of a lot better. But if not, get out there. It's beautiful outside. Get some vitamin D. All right, so basically what we're going to do today is we are going to continue on with our second online unit. We're working on our kinetics and equilibrium unit. Before you proceed any further with this lesson, excuse me, just make sure you did the reaction energy gizmo that I assigned last week, because the gizmo is kind of like the lead into this this lesson. And if you haven't done the gizmo, you might be confused or be behind. So again, just make sure that's done. All right, so let me go ahead and go open up my PowerPoint. There it is. Okay. All right, so if you did the gizmo, the reaction energy gizmo, it was basically all about breaking bonds in reactant molecules and looking out how the energy to break those bonds compared to the energy that was released when the product molecules were formed during a given chemical reaction. So I actually really like this diagram right here. Because it's a really good visual of exactly what happens during the course of any chemical reaction. So in order for any reaction to start, some energy has to go in. It has to be absorbed. And the purpose of that is to break the bonds in the reactant molecules. So anytime you break bonds, it does take some energy. Energy must be absorbed. And the whole purpose of breaking the bonds is to get to this state, where you basically have like these free atoms that are ready to be rearranged and recombined into new product molecules. In this case, it looks like we made carbon dioxide and 2 water molecules. So anytime you go ahead and reform bonds, when bonds are being formed, not broken, there is some amount of energy that is released. And what we're going to do today is really formally talk about how the energy that's absorbed to break bonds compares to the energy that is released when bonds are formed during the course of a chemical reaction. This is what ultimately determines whether a reaction is endo or exothermic, absorbs or releases energy overall. Okay, so we're going to talk a lot today, basically all today, about this, which is delta H. And delta H represents something that is called the heat of reaction. And basically all the heat of reaction is it's a calculation that next time I make a lesson for you, we'll get into a little bit. It's really easy. But it's a representation of the difference in the energy between forming the bonds in your reactants versus breaking them in your, well, sorry, I misspoke, forming the bonds in your products and then breaking the bonds in your reactants. So how does the energy coming out compare to the energy going in? All right, our next lesson, we are going to get into diagrams just like this a lot. I don't want to get into them too much today, other than these graphs, which are called potential energy diagrams, are very good visuals that represent the energy changes that occur over the course of a given chemical reaction. Okay, so what we're looking at right here is this is the graph for an exothermic reaction. How can I tell this is exothermic? Well, I look at the energy's on the y-axis, of my reactant molecules versus the energy of my product molecules. In this case, my products have less energy than my reactants. They're lower, right? Like they're numerically lower on this graph. Since my products have less energy, that implies that energy is being released over the course of the reaction. Some energy has been lost. Thus, this is exothermic. So what we're going to see here is delta H, the heat of reaction, the difference in energy between your products and your reactants. It can either be a positive or a negative value. If a reaction is exothermic, you're going to see a negative delta H associated with that reaction. Why? Well, when we learn next time how to actually calculate delta H, you take your product energy and you subtract from it your reactant energy. Since our products have less energy than our reactants, in this case, our delta H, our change in their energy, the difference in their energy, would be a negative value. So this right here, which I just circled, this little gap here between the reactant line and the product line on this graph, that represents delta H, the difference in the reactant and product energy. All right, I kind of explained it already by looking at an exothermic graph, but next time we will explore these graphs more. This would be a graph called a potential energy diagram for an endothermic reaction, one that absorbs energy overall. You'll notice it's kind of similar, but there's some really big striking differences. First of all, these are our reactants, A plus B here, and this is our product in this case, it made C. I guess I should have said like C plus D since there's two things here, but that doesn't matter. The key is, in this case, our products have more energy than our reactants. They overall are more energetic, which implies that during the course of this reaction, energy overall must have been absorbed. The delta H for endothermic reactions is going to be positive because, again, we'll talk about this next time, you get delta H by taking the product energy and subtracting from it the reaction energy. In this case, our products have more energy than the reactants. If I subtracted whatever value of the reactant energy from that product energy, I would get a positive delta H. Okay, so we're going to end our little talk here today with introducing you to table I. And table I, well, it's something else. This is it in its full glory right there. But basically, it's called cohesive reaction. So it gives the delta H, the difference in energy between the reactants and products, for all of these reactions that you see right here. It does tell you these reactions occur at 101.3 kilopascals, which is standard pressure, but 298 K. It's a little bit above standard temperature. Standard temp is 273 K. Something really big to point out is you'll notice, aside from the actual reactions themselves, they do give you numeric values in kilojoules for the difference in that reaction energy, again, between the products and reactants. Some of these values are negative, which means these are exothermic reactions. And then if you look over here, you can see there are some positive values in there too. So there are some endothermic reactions shown as well. I guess I just put this in here to show you again the whole thing. Okay, so please watch this video to the end. I'm going to give you some really good examples of questions that are going to appear in the Google form that I'm going to ask you to submit. Some of them can be a little tricky, so I'm going to kind of go through that right now. All right, so let's say you have this reaction here. It's a synthesis reaction. You have aluminum plus oxygen, making aluminum oxide. And the first thing we're asked is, can we classify this reaction as endo or exothermic? Well, in order to really figure that out, I would need to know the delta H for this reaction. I would need to find this reaction on table I, and actually, here it is right here. And it shows me the delta H is negative 3,351 kilojoules. Since delta H is negative, it implies that energy was lost or given off over the course of this reaction. So this is an example of an exothermic reaction. Negative delta H means it's exothermic. So now 2, 3, and 4, they ask us basically the same thing, just with varying amounts, 2 moles, 1 mole, or 4 moles of Al2O3. Number 2 says how many kilojoules of energy are released during the formation of 2 moles of aluminum oxide. Well, in order to answer this, what I'm going to have to do is I'm going to have to go back to that balanced chemical equation. So let me just get a little bit of this out of the way. This reaction is written to produce exactly 2 moles. That's what this coefficient means. 4 moles of aluminum plus 3 moles of oxygen make 2 moles of aluminum oxide. So since the amount of aluminum oxide I'm asked about is the exact same amount that the reaction is written for, I can take the value straight from table I, which means that you can just say 3,351 kilojoules of energy are released. You don't need to say the negative. That's just indicating that energy is released as opposed to absorbed. Okay, so then you got to think about it. So it's the same question in number 3. It says how many kilojoules of energy are released during the formation of 1 mole of aluminum oxide? Well, go back to the equation. It's written to produce 2 moles of aluminum oxide. If I only produced 1 mole, or half as many moles, I would release half as much energy. And of course, I did not bring my calculator right next to me, and I don't have my phone anywhere. So you would have to do this on your own, because what I'm going to tell you to do is to figure out the energy released by 1 mole of aluminum oxide, which again is half as much as this equation is written for, is you would take that value you find in table I, which is this, the negative 3,351 kilojoules, and you would have to half it. You would have to divide it by 2. It's gonna be like 1,600 and something. I don't know exactly what it is off the top of my head, but again, you would just divide the number in table I by 2. All right, let's keep going because I don't want to bore you to death. But what if I was asked how much energy is released when I produced 4 moles of aluminum oxide? Since the reaction produces 2 moles, and I want to know how much energy is released when making 4 moles, or twice as much, I would apply a similar logic as to how I answered number 3, except for I would double the heat of reaction given to me in table I. Again, I don't have a calculator. That's a 0, carry the 1, that's a 7. I'm going to go with it 6,702 kilojoules, but I would definitely check my math because I just did that quickly in my head. Okay, so here's our next let's practice, and there's one more after this. It says, according to table I, which substance absorbs energy as it dissolves? All right, let's take care of the dissolves part first. At the bottom of table I, you'll notice there's some of these reactions right here, where there's a little H2O written above the reaction arrow. And basically the purpose of that is to tell us if we see a substance like KNO3 and then a little H2O above the arrow, it's telling us that that substance is being dissolved in water. That's why it's breaking apart into these ions here. So that's the first part. If you want to know the delta H, or the how much energy is absorbed or whatever when something dissolves in water, find those reactions with the little H2O above the arrow. Okay, so one more time, according to table I, which substance absorbs energy as it dissolves? Absorbing energy is endothermic. Endothermic processes have positive delta H values. So I would need to check each of the substances. NaOH, here's my NaOH being dissolved in water. Oop, it's got a negative delta H. It releases energy. It's endothermic. Same thing with my LiBr. Here it is. It's being dissolved in water, but that delta H is negative again, which means it's releasing energy as it dissolves. It's exothermic, which means yes, choice C should be the right answer, and we can confirm that. When NaCl dissolves in water, it actually does release, for every 1 mole of NaCl you dissolve, it does release 3.88, excuse me, it absorbs 3.88 kilojoules of energy. It's the only one of the choices given that has a positive delta H, meaning that process absorbs energy overall. All right, last one. So it says, according to table I, which compound is formed from its elements during an endothermic reaction? Okay. Endothermic reaction, we know that means positive heat of reaction, positive delta H. Please don't let this formed from its elements thing confuse you, because it literally means you're making carbon dioxide and nitric oxide. You're making them from their elements. So let me show you. So if I find an equation that forms CO2, here's CO2 being formed, the element carbon and the element oxygen are coming together to form carbon dioxide gas. So formed from its elements, it just means the actual elements that are part of the compound are being joined together to produce whatever substance is in question. But really, to answer the actual question, they want to know which one of these is an endothermic reaction. This has a negative delta H, which means it's exothermic. If I check NO2, careful, this is NO. This is NO2 that's being formed. We want this one. The element nitrogen comes together with the element oxygen to form NO2. Delta H is a positive value. This is an endothermic process. All right, I'm going to try to have a video chat this week to answer questions, etc. So stay tuned for that information.